Hello, we're the 6U CubeSat team, and we're working to observe the richly dynamic gases flowing around and throughout galaxies known as the circumgalactic medium, or CGM. These gases play an important role in the formation of stars and galaxies. Currently, nobody really knows what the CGM looks like or how it behaves. We plan to change this. We will measure the presence of specific gases around various galaxies. To do this, we are building Maratus, a 6U CubeSat. With the measurements from Maratus, we hope to help answer the specific question: how do galaxies receive the fuel they need to create stars? It starts with the payload, a 3U by 1U Cassegrain style telescope. The payload uses 2 concave mirrors and 6 filters to collect light in the far UV range to observe the circumgalactic medium. It uses a microchannel plate detector, an instrument that allows a nearly constant tracking of photons coming into the telescope from the galaxies we're observing. With this telescope, we can achieve detailed images of faraway galaxies, and the longer we can observe them, the better we'll be able to understand the circumgalactic medium. To hold the telescope and all other components, a machined aluminum chassis will be built. But first, a 3D printed prototype will be used to make decisions on how components fit and are arranged inside the spacecraft. The chassis is made up of 5 pieces and has been designed to withstand the loads and vibrations that Maratus will experience during launch. Along with mounting hardware, this chassis forms the backbone of the spacecraft for all other components to be secured to. In order to communicate with Earth, the spacecraft has to be within range of the UW ground station. While in range, it reorients to point the S-band antenna at the ground station, receives any commands we might send it, then transmits any data it has collected during the mission back down. The key design considerations that were looked at when choosing an orbit were communication bandwidth, communication time, eclipse length, and time in the sun. Lower orbits provided greater bandwidth but lesser communication time. The converse was true for higher orbits. Ultimately, an orbit that balanced communication time and bandwidth was chosen for optimum performance. This decision was verified by visualizing the orbits and using simulations. For this mission, the pointing determination of the spacecraft must be very accurate. Star trackers, magnetometers, and magnetorquers will be utilized to meet this requirement. Magnetometers can measure the Earth's magnetic field and use this information to determine the spacecraft's orientation with respect to the Earth. And magnetorquers create their own magnetic field that can interact with that of the Earth to reorient the spacecraft. Star trackers determine the orientation of the spacecraft by identifying stars in its view and measuring the separation angles between them. The electrical power system manages all power generation, use, and storage on the spacecraft. While in sunlight, the EPS is able to power the spacecraft with solar panels alone, and all extra power goes to charging the batteries. While in eclipse, the batteries power the spacecraft. The batteries are sized to store significantly more than the required energy in order to maintain their health for the duration of the mission. With all these subsystems working together, the Maratus spacecraft will help discover how galaxies are formed and what's happening behind the scenes of the circumgalactic medium. We would like to extend our thanks to our advisors Charlie Kelly and Taylor Reynolds, as well as our stakeholder, Sarah Tuttle, for the help and guidance throughout the design process, and optical engineer Cal Cadleck for designing the telescope.